This is Unit 5, Lesson 4, Part 2, continuing our discussion of points of inflection, concavity of functions, and the second derivative test. We're going to start by giving a formal definition of a point of inflection. So let f be a function that is continuous on an open interval, and let c be a point in the interval. If the graph of f has a tangent line at this point, c f of c, then this point is a point of inflection of the graph of f. If the concavity of f changes from upward to downward or downward to upward at the point. So if c f of c is a point of inflection of the graph, then there's two choices. Either the second derivative of c is 0 or the second derivative of c is undefined. So putting a visual representation to this, here's what we have. So in our first case, we have a function that starts out here as being concave up and then switches to concave down. And what we can see is that along this point right here, we have a, whoops, that's not very good. It's hard to draw lines on this thing. We have a tangent line at this point. This is A, and what we have is that f prime of A is greater than 0, and that f double prime of A will equal 0, because that A there is our inflection point. Okay, so we have that example. The next one, we have an area again, starting out that is concave down. And then it switches over to concave up. And that change happens right there. And what we see at this point is, we'll call this point B, that we actually have a horizontal tangent line there. And what we're going to see is that f prime of B is equal to 0, but f double prime, whoops, that's supposed to be an f. F double prime of B does not exist. Okay? And then our last example, we have concave up here, and then concave down here. Actually, you know what? I'm sorry. This will equal 0 as well, because the derivative of a constant is 0. I'm sorry, I was looking at the wrong point on my notes. So this should be 0 too. The next one, though, is where we're going to have some problems. So here, if I draw my tangent line, what I notice is that this is going to be vertical like that. And so I have a second derivative here. I'll call this point C. That does not exist. And neither does the first derivative either at that point. But we do have a change, and all three of these are inflection points. And this also is an inflection point. Okay, so that fits the definition of our inflection point, where we're changing from one concavity to the other, and our second derivative is either equal to 0 or does not exist. Okay, so let's explore the possibility that a graph could change concavity at a discontinuity, say a vertical tangent line, or where f double prime doesn't exist, such as a cusp. In the case of a vertical tangent line where the x value is not in a domain, then the value x equal p will not be an inflection point. Because remember, whatever we're talking about the function, whether it's its derivative or its second derivative, the points that we find from the first or second derivative have to be part of the original domain of the function. So looking at these graphs, what we have here at P is we have, that is definitely an inflection point because we have F double prime of P is going to equal 0. Okay, but right below it here, we have also a change in concavity because we are concave up here and then concave down there. And we have a situation where F double prime of P does not exist. So we want to be careful. We do have we have an inflection point, but its second derivative doesn't exist. Now that's a little different in the next set of pictures where we do not have an inflection point. And the reason for this is that at this cusp here, what we have is we have a second derivative that does not exist, but the function does not change concavity. It's concave up, concave up. So that is not an inflection point. As well as in the last picture here, we have a vertical tangent line at x equals p. So there's no way we can, even though we have change in concavity here, there's no inflection point. No point of inflection there, because that point P is not in the domain of F. So you want to keep that in mind. Okay. So some important thoughts. We can use a second derivative sign chart to determine the intervals of concavity, just like we used the first derivative sign chart to find intervals of increasing and decreasing. Please remember that the possible points of inflection can be called the critical values of F prime. And remember, concavity can change at a discontinuity, such as a vertical asymptote, but it won't be an inflection point, as we saw in our last picture. In order to classify an x value as an inflection point of the function, the x value must be in the domain. So you want to remember that. Even though we have a change in inflection or in concavity, doesn't automatically mean that we have an inflection point. Okay, so example 3. Determine any points of inflection and discuss the concavity of the graph of f of x equals x to the fourth minus 4x to the third. Okay, so we got to take the first derivative. So we get 4x, I don't want red. Use blue. We have 4x to the third minus 12x squared. Okay, and now what we're going to do is find the second derivative. So we get 12x squared minus 24x. To find possible points of inflection, we're going to set this second derivative equal to 0. And we get two possible points. We get x equals 0 and x equals 2. So now we're going to do a little sign chart here. So our test numbers, so let's add some things to this chart here. So we have a possible inflection point here at 0 and one here at 2. So I am going to take x equals -1, x equals 1, and x equals 3. So finding my sign of f double prime, if I put -1 in my function here, I'll have a negative times a negative. So the sign of my f double prime will be positive. So what does that mean? That means that I should be concave up. And then if I put 1 in my second derivative, I'll have a positive times a negative. So I get a negative. So this will be concave down. And of course it's 0 at 0. And then when I go to 3, I have a positive times a positive, so I get a positive. So I am again concave up. And of course it's 0 at 2. So a couple conclusions here. Number 1 is I have 2 points of inflection. I have a change of concavity. And these points are in the domain of the original function, 0, 0, and 2, negative 16. Now, I can say also that f is concave up on negative infinity to 0, and also from 2 to infinity. And my reason is that my derivative, my second derivative, is greater than 0. And finally, I have one section where the graph is concave down. And that is at 0 to 2. And my reasoning again is that my second derivative is going to be less than 0. Okay, so that's how you find the concavity using the second derivative. Okay, example 4. Find the inflection points and the open intervals of concavity. Justify your answer. And that's exactly what we did in the last one as well. So here's our function. G of x equals 1/2 x plus sine x on 0 to 2 pi. Okay, so again, what we're going to do first is we're going to take the first derivative. So g prime of x is going to equal 1/2 plus cosine x. And then g double prime of x is going to be negative sine x. Okay, and we're going to set that equal to 0. And in the unit circle, the only place that sine x is 0, not at the endpoints, is at pi. And so making our little sign chart here, we're going to have 0 here, we're going to have 2 pi here, and in the middle is, of course, pi. So picking my x values, I'm going to use pi over 2 and 3 pi over 2. Real easy ones to use. And so my f double prime sign, and then below I'm going to put my f direction. Okay, so if I substitute pi over 2 in my second derivative here, pi over 2 gives me a 1, but there's a negative sign in front of it, so this is going to be negative, which means my function's direction is going to change to being concave down. And then at 3 pi over 2, sine of 3 pi over 2 is negative 1, and negative 1 is positive. So the function is going to change direction and become concave up there. Okay, so I need to find where my inflection point is, and I didn't talk about this in the last example. I just kind of wrote them down, but I have to substitute my critical number here into my original function. So I get 1/2 times pi plus sine of pi. And that simplifies to pi over 2 because sine of pi is, of course, 0. Okay, so here are my conclusions. Number 1, I have an inflection point at pi over 2. The next thing is I have an area that is concave down, so g of x is concave down. On 0 to pi, since g double prime of x is less than 0. And then I have one section that of g that is concave up. And that is from pi to 2 pi, since g double prime of x is greater than 0. Okay, so that's how we justify it. I'm going to do these last two examples and then stop the video, and we'll finish up with the second derivative test in the second video. Okay, number 5, use a calculator to find how many times the graph of y equals x squared minus 3 plus sine 2x minus 1 changes concavity on the interval from 0 to 2 pi. Okay, so what we need to do is, the easiest way I think to do this one is to find the second derivative and then find the zeros of the second derivative, and then we can compare it to the original function. So let's go ahead and find the two derivatives. So y prime is going to equal 2x, the 3 will go to 0, I have to use the chain rule there, so that's going to give me plus 2 cosine 2x minus 1, and then to take the second derivative, I'm going to get 2, and then I'm going to do minus, and again do the chain rule, so minus 4 sine 2x minus 1. Now what I'm looking for is where this equals 0. So that's what I'm going to put in my calculator. So I did it in the 84. You can do this in the Inspire. What's nice about the Inspire is once you have the derivative or the function in, you can just hit trace and it'll give you the zeros. So what I'm going to do is I'm actually going to search for the zeros. So second trace 0, and I have to do it 4 times. I'm going to start way over here to be systematic. Okay, so be on either side of the 0 here. And so there is 1 0 at, oh, that's the guess. I'm like, wait, that's not right. At 0.7618. And you're just going to do that and write all 4 of those zeros down. So I'm going to go ahead and do that. So you have x equals 0.7618. X equals 1.809, x equals 3.903, and x equals 4.951. And of course, we're restricting ourselves to the unit circle, 0 to 2 pi. So these, we have 4 zeros, so it changes concavity 4 times. Now just to verify that, okay, next problem. Using a calculator, find the values of x at which the graph of y equals e to the x squared changes concavity. Okay, so just like the last example, what we're going to do is take the first and second derivative. So we get, and we're going to have to use the product rule here, e to the x squared plus 2x e to the x. And then to get the second derivative, we're going to have to use the product rule in each of the terms above. So we have e to the x squared plus 2x e to the x. That will take care of that term. And then the next term is going to be 2e to the x plus 2x e to the x. Now I have some like terms, so I can simplify this a little bit. So I get e to the x squared plus 4x e to the x plus 2 e to the x. And again, we're going to set that equal to 0 and find our zeros. So putting that in our calculator, we have this picture. And I do only have 2 zeros because eventually the exponential growth takes over here and it's not going to come back down. So finding my zeros here, the same idea. I'm going to go through and do that real quick. I'll just do one here. So I'll just do this one. Negative there. And then I'm positive there. And so the first 0 is at negative 0.856. And then there's another one further back here. So finding both of those, there are 2 zeros. X equals negative 3.414 and x equals negative 0.586. So there's 2 times. Okay, and then we'll finish our discussion of this with the second derivative test in the final video.